Could have done some more on those carbonyls, but A, will save that for the worksheet, and B, they're much of a muchness. A lot of times you will see people say, well, if you've got an aldehyde, then you will see the result of losing that H. Well, of course, losing that H is the same thing we've just seen, making the acylium ion that's just one less than the molecular ion. But now let's go to a different type of carbonyl group, those that are associated with a carboxylic acid. And I'll do two of these. Start off with propanoic acid, a nice small one. There's the spectrum of it. Let's have a look at the interesting peaks that we might have. Well, first of all, we have the molecular ion, right? M equals 74 right there. Nice big dominant peak. So as was the case with the aldehydes and ketones, a lot of times you will see a nice strong molecular ion for acid groups. We got these other peaks here that I'm going to focus on immediately. We got the base peak at 28. We got a fairly significant peak there at 29, then a 45, then at 57. Okay, now the one at 29 we've seen many times before, CH3CH2 plus. That's a pretty reasonable assignation. But how about these other ones? Well, there is propanoic acid, 1, 2, 3 carbons. There's the O and the OH. Okay, you can see where the ethyl is going to come from, right? The CH3CH2 plus, cleaving that bond there. However, let's think about that bond cleavage in a way analogous to what we've already done with the alcohols and with the ketones, and that is, let's get the involvement of the oxygen. Okay, so we'll break here. Now remember, of course, this oxygen, it's a radical cation, so we'll see the usual electron movement. I'm not going into detail, but when we do break it, we're going to make this a acylium ion that's even more complicated than the acylium ion because it's got the OH there. So exactly the same idea, breaking here, radical there, cation stays on here. Okay, mass of that little pretty thing is 45, right? Okay, let's check ourselves. I do want to make sure you're seeing these masses. One time when I was teaching mass spec last millennium, which was last time I even really thought about mass spec too much, I sort of looked at it and said, oh, of course, it's got mass 45. And I remember one of the students looking at me with this disgusted look on their face. So anyway, we got 16 plus a carbon is 28 plus another oxygen takes us 28 plus 16 is 44 plus 1 is 45. So that's the peak of 45 associated with cleaving there. Now let's cleave and lose the OH radical there. And so what we're seeing there is the CH3CH2C, just as we were expecting, plus the oxygen. So CH315 plus CH229 plus a carbon 41 plus an oxygen 57. So there's the one at 57. Okay. Now we still have another bond between the carbonyl carbon and something else. In this case, it goes to the oxygen. In this case, it goes to another carbon. Well, let's cleave those bonds, and it doesn't matter whether we cleave that one or whether we cleave this one. We're going to have this lovely CO plus cation. Okay, break it there, CO plus, break it there, CO plus. Okay, and this has a mass of 28, right there, that base peak there. Okay, so 28, a very common peak in acids associated with the CO triple bond that just comes effectively from stripping everything away from the carbon double bonded to the oxygen. Now there's one other peak that I want to hit before we move on, and that's the one here at 73. Okay, that's one less than the molecular ion. Can you think of a hydrogen in this propanoic acid, little hint there, that might be the one that fragments off, leaving you with a significant peak, one less than the molecular ion? And the answer is, of course, you always lose the acidic H, or you frequently can lose the acidic H in an acid fragmentation, leaving you with one less than the molecular ion. I am going to do one more acid because, well as forming the acylium cations that we've talked about for the last couple of movies, and as well as losing the acidic hydrogens, there is for these larger acids a very, very distinctive peak that is often wonderfully diagnostic that you have a larger acid. So let's think about butanoic acid. Okay, here's the spectrum of butanoic acid. The mass is 88, so our molecular ion at 88, you can just see it there, and the result of losing the acidic hydrogen, one less than it there at 87. Here's the structure. We know we're going to expect the acylium ions caused by breaking these two bonds here, and so when we break the bond to the OH, we're going to get a peak at 17 less than the molar mass, so that's 71 down there, and you can just see the 71. If we break here, we're effectively going to lose the 43 propyl down there, and so we will end up with a peak at 45 right there. So there's that peak, and of course that 45 acylium ion is going to be present in virtually every mass spec of an acid. We can see we got some other old favorites. Here's 28 there, that's the CO triple bond. There's 29, you can see 29 coming from fragmenting to give us a CH3CH2 plus. We got 43 right there coming from CH3CH2 CH2 plus. Okay, but there's two dominating peaks that we haven't done anything about yet. The first one of those is 60, and this is the one that is extremely diagnostic of acids. Larger acids and esters, you will have that nice peak at 60. Now play around with this for a while and see if you can figure out how to get a fragment that has a molar mass of 60. And if any of you come up with it in a rational, sane way, I will be dead impressed. So I'm going to tell you where it comes from. It comes from the so-called Levity Rearrangement. Again, this is something that will take place in acids, it will take place in esters. Levity Rearrangement relies on having enough carbons past that acid carbon, and to illustrate it here, I'm really emphasizing it by drawing the structure as I have. There's the acid group, which of course has the radical cation on the oxygen, CH3, 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 CH2, CH2, and then a CH3, emphasizing one of these hydrogens. So you need that hydrogen in that six-membered ring. So you have to have an acid or an ester that's big enough to give you this species here. Okay. Now, the electron rearrangement that takes place is relatively familiar. First of all, we break a bond between the carbon and the hydrogen to make a bond between the oxygen and the hydrogen. We've seen this a couple of times before, specifically for losing water. Okay. Now, at that same time, within the carbon ring, you have pi electrons come from the carbon-oxygen bond down here to make a double bond to this carbon. This carbon at this stage says, hey, that would give me 5 bonds, so I'm going to lose the electrons to this carbon, which it then loses to form a double bond to the carbon that lost the hydrogen. Okay, so we end up making this. We kick out this, which I've drawn as a molecule. It could quite easily leave as a radical, okay, but we're left behind with this cation here. And this cation here has got the original acid group that's got protonated, the C double bond O, and then a double bond to one of the carbons next to it, okay. You have to have an acid that's big enough to provide this hydrogen, okay. Bigger acids than butanoic acids, you have more of a chain going on here, you just create more alkenes, bigger alkenes. Okay, now let's look at this fragment in green here, and I bet you can guess what its molar mass is. We got 17 plus 12 is 29, plus 14 is 43, plus 16 is 59, plus 1 is 60. So that massive peak at 60, thanks to a Levity rearrangement, that will be there in many, many acids, bigger than butanoic acid, as long as you have the capability of making this pseudo six-membered ring here. And you'll also see some weird, strange, anomalous peak and a lot of esters due to, again, a Levity rearrangement. Now, the other thing that you will often see in the longer acid change is you'll start to see fragmentation at the the end of the chain away from the acid. So in other words, if we have a fragmentation here, the radical goes onto the CH3 bit there, and then we have the cation here. So we make the cation drawn here. This has a mass of 73. Essentially, the original mass, 88, minus that CH3 at the end. 88 minus 15 is 73. We could also expect to see a peak at 59 as we lose another CH2, and then another one at 47. And you can kind of see the 57 and the 47 as we progressively lose those carbons. And again, seeing that sort of chain fragmentation is again something diagnostic of some of the bigger acids. So there we are. We've talked about all of the carbon-oxygen interesting bits, essentially fragmentations associated with being next to the carbon-oxygen single bond or double bond to give you those nice extra stable cations, and then some other special things associated with alcohols and with acids. A lot of this, more than you would expect at A level.